6. Okay. Wow, which number video is this? This is number 5. Hopefully you're skipping to the parts where you're wanting to answer or get questions answered. And again, hopefully if you need a lot more help on these, that you're getting more out of the slightly longer descriptions. If not, maybe I'll just put these notes online so you guys can have access to those, just to be able to look over them so you don't have to necessarily listen to me babble the whole time. So, given 4x equals the square root of 4 minus 5x, find the average rate of change between x equals -1 and x equals 0. Between x equals 1 and x equals -1 and x equals 0. So, finding average rate of change. Average rate of change is another way of describing slope. This graph, I'm going to draw it roughly. You guys kind of know where it is because you've had that section 3.5. Anyway, no, it's not there. Anyway, wherever this graph is, between -1 and 0, this graph curves. But to find its average rate of change, what we're going to find is the slope of that line, technically called a secant line, that's straight through it. So if we zoomed in here, we'd have a curve here, and instead of finding the average rate of change between, or the rate of change between all of these little points, we're going to find the rate of change of the values along that line, and that's going to be our average. Well, because we're just finding slope, the average rate of change formula should look familiar. F of x2 minus f of x1 over x2 minus x1. It might not jump out at you, but this is f of x, that's a y value. F of x1 is another y value. This is y minus y over x minus x. This is slope. y2 minus y1 over x2 minus x1. It's just slope in function notation. Don't let your textbook convince you that this is some new fancy formula. This is slope. Now, we've been given the x values. They just didn't tell us the y values. The extra step is we have to find those y values. We have to go find f of 0 and f of -1 and put those in. So f of 0, put a 0 in there. Square root of 4 minus 5 times 0 is the square root of 4 is 2. Put in the -1. Square root of 4 minus 5 times -1 is the square root of, that's 9, which is 3. So the difference between the function values, f of f of 0, minus f of -1 over 0 minus -1, to put the values into this formula. F of 0 was 2. F of -1 was 3. 0 minus -1, so 0 plus 1. So that's -1 over 1. The average rate of change is -1. So this line is dropping at a slope of -1, which it frankly kind of looks like it does. So the big thing about average rate of change is, remember, average rate of change is slope. It's just slope. Slope of the line between those two values. That's why people often ask if you can have this formula on your tests. Well, no, but you don't need it because you know slope. You know y2 minus y1 over x2 minus x1. It's just slope. It's just in function notation, so it looks a little funky. Okay, I want to speed too much through these, but I don't want to take up your entire life listening to me talk. So consider the function. Okay, you'll see these types of problems fairly often where you're given a relationship, given a model. You looked at your section on doing regression with lines and quadratics and whatnot. That's how these are found. That's how these are found. You take data from whatever your scenario is and you build a model, and boom, you have your model. So when you're in industry or whatever you happen to be doing, you'll be able to come up with models using that regression tool. If you've ever wondered where these little formulas come from in these word problems, it's not magic. They come from that regression tool a fairly good amount of the time. So this function models the flight of a ball kicked through the air, where h is the height, so this h of d is the height of the ball, and d is the horizontal distance from where the ball is kicked. So this graph actually has a very nice physical representation. That's the path of the ball, where d is the distance, and h is the just plain height. So it's almost a picture of the actual path of the ball, which you got to admit's fun. Well, I guess you don't have to admit that that's fun, but anyway. So find the maximum height. Well, where's the maximum height? Hopefully I heard the entire internet just say vertex. Yes, vertex. So the d value of the vertex, the distance at which the vertex occurs, is that same negative b over 2a. So negative 20 or 2.6 over 2 times negative 0.16 is going to give you the value of that vertex. I again don't want to spend too much time having you watch me do this. 32. But that's going to give you a value for d. I'm again just going to call it dv, the distance at which your vertex occurs. Now that's going to be where it happens, like how many feet it takes for it to reach its maximum height. If you want to know what the actual height is, and we're asked find the maximum actual height, well, what are you going to do with this value to get the actual maximum height? You're going to put it into the function and calculate the actual maximum height. Let's see, we'll then ask to find if the ball clears an 8-foot fence placed 15 feet from where it was kicked. So 15 feet from where it was kicked at d equals 15, there's a fence that's 8 high, and the question is, does it clear that height? Well, if this maximum height is more than 8, that doesn't necessarily mean it's going to clear the fence. It'll only clear the fence if it's still above 8 after 15 feet. I mean, this thing could go up 20 feet and come back down so fast that it's not going to get over this fence. To know if it's higher than the fence at 15 feet, all we want to do is ask, what is the height at 15 feet? So negative 0.16 times 15 squared plus 2.6 times 15 plus 1. That's just a number. You've got very fancy calculators. Find out what that number is. If it's more than 8, it's above the fence. If it's less than 8, it's below the fence. It's just a yes or no question at that point. But make sure you separate the idea of where is the vertex versus this fence. By the way, you could also be asked on this question, how far does it go out before it hits the ground? Well, hits the ground is height equals 0, so if you want to know where it hits the ground, let the function for height equal 0, solve for d. So you'll see questions like this. Sometimes you'll be asked for particular values. Sometimes you'll be asked for maxes. Sometimes you'll be asked for where things zero out. You want to be able to approach all of those questions. And again, you can calculate this value out. You can calculate this value out and put that in there. I'm just trying to help make sure your setups are good and solid. Let's see. Number 8, bus fare question. Bus fare in the city is normally $1.25 per ride, I assume. Yeah, normally $1.25 per ride. But if you use the bus a lot, you have the option of buying a monthly coupon book for $10. So you can either do this, it's option 1. Option 2, you can pay $10, and then it will reduce the cost of the ride to 50 cents. So, and 50 cents per ride. Oops. ride. Determine algebraically the number of bus rides one would take in order for each option to have the same, to cost the same in a given month. And why would we want to know that? If you're riding the bus once in a month, you're not going to buy the $10 thing. That would you'd be wasting your money. Just pay your $1.25, ride the bus once. If you're going to ride the bus 3 times a day all month, so that could be, what, 90 some odd times, you're going to want to spend that $10 and get those cheaper rides. But the question of how many rides per month does it take this to be a better deal than that? You know, am I riding the bus often enough to make it economical for me to buy the pass, or should I just be paying per ride? If we know when they're equal, if we go more than that, buy the coupon book. If we're going to be using the bus less than that, pay per ride. So it's a common kind of, where's the equilibrium, so I know which economic thing to use. So we want to know when these are the same. So if you're paying per ride, you're going to pay $1.25 for every ride. I'm going to use R for the number of rides. It's always good to say that. Let R equal the number of rides in a month. It's a good tip, by the way. If you don't know exactly what your variable stands for, figure out what your variable stands for. You can't write an equation without knowing what it means. So when is $1.25 per ride the same as $10 plus 50 cents per ride? And then we just need to solve this. So subtract the 50.5R, subtract the 0.5R. So we get, what do we get, 75? 0.75R equals 10. Divide by the 0.75. Again, you guys can solve this stuff. The trick is always getting them set up, isn't it? I'm going to move that decimal over twice because I feel like it. Over 75. Reduce this fraction. I don't know what I don't feel like reducing fractions today. That's what, 200 over 15. Is that even right? 20. Yeah, 200 over 15. Fine. And then divide by 5 again. So many thirds. What is that divided by 5? 40 thirds. So 13 1/3 rides. If I did something weird in there, forgive me. It's been a lot of videos. So at 13 1/3 rides, they will cost the same. Well, of course, you're never going to ride 13 1/3 times. But at 13 rides, that means $1.25 per ride is going to be slightly better. At 14 rides, buying the coupon book makes more sense. So if you're riding, 15 times in a month, buy the coupon book. If you're riding 10 times in a month, don't buy the coupon book. If you're riding 20 times in a month, very much buy the coupon book. So it's really a nice way that people establish what kind of choice is better when you're doing things like buying insurance, when you're buying cell phone plans, mortgage plans, all those kind of things. It's the type of way that you use a lot of this material. Okay. Oops. Always remember I'm trying to speed up. I think I did a video on this truck problem a while ago, so look that up if you want more specific. But just real quick, you've got a highway and a truck that's been on the highway for 5 minutes going, what, 55 miles an hour? Yep, 55 miles per hour. And it's been doing that 55 miles an hour for 10 minutes. I think the numbers were different in the other version of this problem, but that's okay. So after those 10 minutes, the car enters the freeway going 70 miles an hour. They should not be driving that fast. So clearly they have a fast little car. And they are going 70 miles an hour. I always recommend drawing diagrams, by the way, if you haven't noticed that yet. Involves a lot more parts of your brain, brings a lot of other skills to bear, so it's a good habit to be in. And you want to know when they pass. When they pass means you want to know when they're equal. So when is the truck's distance equal to the car's distance? So when is the truck's distance equal to the car's distance? Well, the car's distance, all distance, you might remember, distance is rate times time. I always call this formula DIRT. Distance is I, rate times time, DIRT. So the car's distance is just its rate, 70 miles an hour, times the time. You got to be a little careful, though, because this time is in minutes. How many hours is 10 minutes? It's 1/6. Let me back up. Sorry, went too fast there for myself. The car is going 70 miles an hour. We're asked how long does it take for them to reach each other? That's what we don't know. We'll use the 1/6 in a minute. Sorry, I jumped the gun there. So 70 miles an hour for some amount of time. The truck is going 55 miles an hour for the same time that the car is going, but it had a 10-minute head start. So it had an additional 1/6 of an hour. I told you that 1/6 was going to come up. Sorry about that. So when is the 70 miles an hour for t minutes equal to 55 miles an hour for t, technically hours, plus the 1/6 of an hour? I think I talked on the other video for a problem like this, that if you wanted, you could keep the 10 minutes as 10 minutes, but then you'd have to change these into miles per minute, and you probably don't want to do that. So changing the minutes is generally easier. And then just solve this. Distribute your 55, move the 55t over, divide that off, solve the rest of that, and you'll have the number of minutes necessary for the car to catch up with the truck. If you want more on that, I know there's a truck video on the website, so you can check that out. Let's see, the last couple, these tend to be fairly nice. Piecewise functions, mostly I'm having this here, just kind of the whole, make sure you know how to read piecewise functions. They come up every now and again. This function has the rule x squared plus 5x. When x is less than -5, it uses the rule f of x equals 50. When x is between 5, or -5 and 5, including -5, and x plus 2 squared plus 1 if x is greater than or equal to 5. So you remember functions, every single input has to have only one output. So this f of -10, we can't just willy-nilly put the -10 into all of these. We'll get possibly 3 different answers, and those 3 different answers will make it not a function. Every question has to have one answer. Every input has to have one output. So this has to tell us when to use each of these functions. This -10 is that x value, that -10, less than -5, between -5 and 5, or greater than or equal to 5. Well, it's less than -5. That means we have to use this rule. So -10 squared plus 5 times -10 is 100 minus 50 is 50. So f of -10 is 50. And we ignore the other rules because they weren't meaningful. You're then asked what f of 3. 3 is between -5 and 5, so we use this rule. This rule says when you're between -5 and 5, the function value is 50. Not 50 times x. There's no x involved. If you're between here, the function's going to output a 50. So the answer is also 50. F of 5. 5, again, you stop and figure out which one of these groups is the 5 in. Sorry, f of 5. Which one of these sets is the 5 in? Well, 5 isn't less than -5. It's not strictly less than 5. 5 is greater than or equal to 5, so we have to use this rule. So we put it in there. 5 plus 2 squared plus 1 is 7 squared plus 1 is 49 plus 1. It's again 50. I did that for fun. Kind of made them all be 50 because I get, I have fun. But the key to piecewise functions is making sure you look at the x value. The x value will go with one of the groups. This part of the domain goes with that rule. This part of the domain goes with that rule. This part of the domain goes with that rule for as many types of rules that they have. So hopefully you've played enough with piecewise functions that you're comfortable with that. But if you're not, I want to make sure you are because they will come up from time to time. Okay, last one. Okay, yeah, last one. So we have a graph here. That is a graph of a function. We know it's a function because it passes the vertical line test. We can grab a couple points on that function if we want. This point looks like 2, 0. This point looks like 1, 2, 3. It's hard to say. That might be 4, 4. Whenever you're picking points off a graph like this, you're approximating. Go ahead and approximate. 1, 2, 3, 4. That's at 0, 4. And this point looks like it's at 1, 2, 3, 4, 0. Negative 4, 0 anyway. So those are the points that I'm going to assume are there. Again, label your points. If your points are properly labeled, it's hard to argue with you. Now, this is f. We are asked to graph f of x minus 1 plus 3. So your section 3.5 talked about those translations, so it's important to know what these do. Subtracting that 1 inside is going to move the function that way to the right 1 unit. And when you read that section, you got used to the fact that everything happening inside was backwards. Adding the 3 outside is going to lift us up 3 units. And those are the translations that we have to deal with. So each one of these points is going to go over 1 and up 3, over 1 and up 3, over 1 and up 3, over 1 and up 3. So for example, this point here, the negative 4, 0, it's going to go from negative 4, 0 over 1 because of that one, and up 3. So it's going to end up at negative 3, because it went this way 1, up 3, it's going to be 3. The point here at 0, 4, it's going to do a similar thing. It's going to go that way 1 and up 3. So it's going to be at an x value of 1. We're adding 1 to the x value. The y value is going up 3, so it's going to be at 1, 7. Right there. And every other point in this graph is going to do the same thing. So our image is just going to shift over and up. These points are going to do the same thing, as are all of the others. So that point at 2, 0 is going to go over 1 to an x value of 3, and up 3 to an y value of 3, and it's going to be at a nice 3, 3. And so is every other value along the way. 4, 4, same thing. That way 1 to an x value of 5, and up 3 to a y value of 7. So we're just following the translations. If we had something like say a 3 out, not a 3, I don't want to use a 3 again, a 2 out here, that 2 would be a stretch. So we'd be taking our y values, that y value is a function value, so instead of just adding the 3, we'd multiply it by 2 and then add 3. So it would become 8, 9, 10, 11. So it would be up at 5, 11. So we're just performing whatever the multiplication and addition is on the outside. Same thing with the inside, except remembering that they happen backwards. This minus 1 turned into adding 1. If there was a 5 there, we'd be dividing all of our x values by 5 and compressing this. So you want to be able to handle those nice, simple or comparatively simple translations. I'm not going to give you nasty problems from 3.5, but knowing how to handle your translations nicely is one of our important tools. Okay, I think that's the last one. I know these were long. Again, if you want anything more particular spelled out or something gone a little more into, let me know. Again, hopefully the extra babbling was helpful. And if there's anything else you guys need, please let me know.